Okay, in this video we're going to review the concept of marginal cost and marginal revenue, but combine it with the idea of local linear approximations. So this is all from Chapter 2, in particular Section 2.5, and I'm going to split this video up into two parts. So in the first part we're going to talk about what it means to be a local linear approximation. And in the second part, which will actually be in another video, we're going to do a particular example of local linear approximation, but in the context of marginal cost and marginal revenue. So let's start off here with this function, f. I'm going to tell you about what it means to be a local linear approximation to this function. And let's say you have the graph, it's right here, and that you furthermore know one point on that graph, a comma f of a. Okay, so there's one point on the graph. It's a comma f of a. Okay, so right here on the y-axis, this is the value. Oops, f of a. Okay, so again, this is known. This is something you know right in the beginning, or at least you assume you know it. And the question is, can you know other values of the function? For example, at x equals b. So what is this value? And we're assuming that this time we can't just plug it in and get it. Alright, so this is question mark. We don't know. So it's unknown. Alright. So again, the question is, if we know a value of the function at a single point, can we know another one? And the answer is yes, as long as you know the derivative at this point x equals a. So what is the derivative again? It's the slope of the tangent line at that point. So let's draw the tangent line at that point right here. So here we go. Color that in. So that point is still a comma f of a. That's where this line is tangent to the graph, but its slope is precisely the derivative of this function. And so because we know the slope and we know a point that's on the graph, we can write its formula down using the point slope formula. That of course is just y minus some point y0 equals the slope times x minus some x value. But what are those x values? We know that. What is that x value? It's just a, because that's the x value we know we can plug in. What's the y value? It's the corresponding point on the y value for that output for that input, f of a. And now this time the slope is simply the derivative of the function at x equals a. Okay? So this is the formula for this line here. So now the question is, how can we use this formula to get a reasonable approximation for the function at b, at the point x equals b? And it's actually really simple. You see, this line is pretty close to the graph. In fact, it touches it exactly at x equals a, but otherwise, at least in this function, it's pretty close. And so instead of taking this value, instead of taking the exact value of the graph, because we don't know it, we're going to take the value on the line, this y value on the line. So this green point right here. And what is that green point? Well, you see, how do I get it? All I do is I plug b, but instead of plugging it into f, I plug it into this formula for the line. So that y value is exactly, well, solving for y, I get f of a plus f prime at a but now I plug in the value b. So actually, let me make that a new color so you can see that. B minus a. Okay, so this is the x value we plug in to now this linear function. And we're going to call this thing our approximation for f of b. In other words, for this pink point. Alright? Why is that? Because this line is reasonably close to the graph of the function. As you can see, as you go further away from the known point A, if we push b further down over here, for example, then the gap between the line and the function is larger. And so that's why we call this a local approximation, because it only works if b is close enough to a. Of course, you could take b a little bit below a and the idea would be the same. But the point is, we're using this line to approximate values of the function f, which may not be a line. And this is how local linear approximation works.